is Hasheesh, and I'm a senior software engineer at Cadence. Now, regarding today's agenda, we will be discussing the importance of pre-silicon verification and the verification flows, how to prepare to verify a Cadence cell device, some interesting scenarios that we think are important to target, some information about our VIP, which we provide at Cadence, and how to conclude the verification flow. First of all, why should we do a pre-silicon verification? Pre-silicon is basically cheaper, faster, and more effective than post-silicon verification, since you can easily catch bugs before production. You can catch bugs earlier. You can easily show the design because it's easier to share software than sharing hardware. And post-silicon verification, you will actually need to print, synthesize the IP before being able to share it. However, in pre-silicon, you are mostly verifying via simulation, which makes it easy to share because it's much easier to share software than sharing hardware. And by combining all these facts, it reduces the cost since it's much less likely to discover a bug post-production. Now, how would we go about verification? As one would say, 1,000 miles journey begins with a step. The first step in verification is reading the specification and understanding it. After reading the specification, we need to formulate an attack plan. We create our plan by checking the IP specification, the rules, the various request types, what kind of illegal scenarios or what kind of coverage points do we need to target. To do that, at Cadence, we provide software called vManager that enables you of creating a vPlan and a test plan using the PDF of the spec. After preparing your plan, you understood the spec, you will need to start working on your testing. That starts with preparing the test bench topology, which you could either build as a normal system Verilog topology, normal Verilog topology, or preferably you could create a UVM topology. After you have your test bench ready, you can start writing sequences. Sequences are basically network level transactions between the devices. And by doing them, you can target certain scenarios. For example, an account device, there's a frame called data frame. You can send a data frame to see that your IP is handling, sending, and receiving the CAN frame, the data frame correctly. Now, when writing these sequences, you will need to check that your tests are sufficient. How would you do that? That is done via coverage. Coverage is basically the functional capabilities of a device. So, for example, in a CAN device, you have the identifier. You have a range of values for the identifier. So you might want to check that you covered all possible values of the identifier. You have various lengths of the frame for data frame sizes. So you might want to check multiple sizes of the data frame. So after writing your sequences, you will check them against your coverage. If they are sufficient, you can conclude. However, if they are not, you will need to refine your constraint. By refining constraint, we are either talking about adding more tests or modifying the randomizations of your existing tests. And you can here will get into a feedback loop of writing tests, modifying tests, checking coverage until you are satisfied with the results you have at hand. And then you can say, okay, I'm done. I can we are done. Now, preparing to verify a CAN cell. CAN cell is relatively a new IP. CAN cell is by definition backward compatible with CAN format and CAN FD format. So the first step of verifying CAN cell format is to understand the basic flows of CAN formats and CAN FD formats. That could be includes the classical frame formats, which are remote, remote extended, data, data extended, error frames, overload frames, and uh, the FD frames and other encoding methodologies, like the dynamic stuffing encoding in classical CAN, the static CRC stuff encoding in FD CAN, and the details about switching data rate in CAN FD frames. After finishing the understanding of these formats of CAN and CAN FD, we can start understanding the new challenges a CAN Excel provides, which are the Excel formats and the new stuffing methodology that is adopted by CAN Excel. Now, in this slide, you can see basically all basic types of frames that are supported by CAN Excel device, which are remote extended, data extended, FD frame, FD extended frame, and Excel frame. Now, here you can see that an FD frame has a bit called reserve. If this bit is set as high, as recessive in this case, it will be interpreted as Excel frame. So this bit is no longer reserved in a CAN Excel, and a new reserved bit called reserved Excel is introduced. CAN Excel, as demonstrated earlier in the discussions, has many new fields like VCID, address field, STT, that could be freely randomized in your network to achieve multiple usages. Now, here we have some interesting scenarios that we think that are important to cover when you're testing your CAN IP, your CAN Excel IP. The first of which your compliance with classical CAN. So your CAN Excel device will surely needs to be able to transmit remote and data frames correctly. And if it does support error and overflowed frames, it needs to be send them correctly and interpret them if it's enabled. Now, in classical CAN device, there's an edge case that is a data frame with no data. It's technically possible to send a data frame with the data length count of 0. This will in turn send a data frame with 0 data. The same is in FD frames. It's technically possible to send an FD data frame with a data length count of 0, which will send an FD frame with no data. These are kind of important because when you say data frame, you would expect you have data. But in these cases, you are doing a data frame, but with no data. Now, in CAN Excel and CAN FD, there's a slight difference in FD frames regarding the bit rate switch. In CAN FD, there are technically 2 prescalers allowed on your device. So, and you have a prescaler for the nominal phase and a prescaler for the data phase. However, in Excel, both phases, nominal and data phase, share a single prescaler, while they have different phase 1, phase 2, and propagation timings. So when you do an FD frame on a CAN Excel device, while the timing will be different depending on phase 1, phase 2, and propagation configurations of your IP, the prescaler will still be the same. You will not get the ability to use 2 prescalers in CAN Excel. Second, another interesting scenario in CAN Excel is basically the RS. And now the RS here is basically the remote substitute field. In all the frame formats, if it was sent as 1, as CAN Excel is a standard ID format, this would be in turn always be interpreted as remote. However, in CAN Excel, even if you set the remote substitute field as 1, it will be still be interpreted as an Excel data frame as long as you are sending FD and Excel bits as 1. Now, in CAN Excel, there are some optional bits and tolerances regarding some bits. For example, a receiver could technically receive a frame with no DH1 bit. So a frame will immediately transitions from a DH1 to a DL1 with no DH2 bit. Also, it's possible that the DH1 bit itself be repeated from 1 time to 6 times, and a receiver needs to accommodate that. So there are 2 bits called 3 bits back to back that are DH1, DH2, DH1, DL1. It's basically possible to transition immediately from DH2 to DL1, or to have multiple 1 bits, sets of bits from 1 to 6 times between the DH2 and the DL1. Also, there's another optional bit called AH1, and if it's not received, the receiver should behave normal. So it's an optional. Furthermore, and the final interesting scenario, in our opinion, is an Excel frame with data length count equal to 0. Now, an Excel frame will always contain data because the size of data is calculated in the formula of DLC plus 1. So if you send a data length count of 0, an Excel frame will be sent with a size of 1 byte. So it's impossible to send an Excel frame with no data. Now regarding our VIP provides many features, including but not limited to its FD compliant. So you could use our devices, VIP device, to test a CAN FD device IP. It's Excel compliant. It has the compliance test suite as defined by the ISO 16845-1 spec. So we have a complete library of compliance test suite that are usable, and you can use them in testing your IP devices. Our VIP provides many flexible configurations and reconfigurations on the fly while doing any tests. For example, you could change the timing parameters of phase 1, phase 2 during runtime, and you can automatically on the fly enable, disable retransmissions, change the fault state of the agent from error active to very passive, and a lot of other configurations. Now, our VIP supports languages that are System, Verilog, and UVM. So if you want to use our VIP, you will need to use either System, Verilog, or UVM. We provide you the ability to generate random traffic to the network quite easily via predefined transactions. Our VIP contains many checks on the compliance of the protocol. For example, if your dot or IP sends an invalid frame, we will detect it and notify you about the invalid format. Furthermore, our VIP provides you with many callbacks that you can use to either build, to synchronize your test bench, to create scoreboards, to do side checkers. The sky's is the limit using callbacks. We also provide you with out-of-the-box coverage that is built in System Verilog. So you could use our coverage to say as a deciding factor if the testing is sufficient or more testing is needed. Finally, is the concluding of the verification. Now, how would you say, okay, I'm done, I've concluded my verification? The first is to basically have a full functional coverage, which are the classical CAN features, the CAN FD features, and the CAN XL features, which can be done by checking all frame formats with various constants done on each frame. We also recommend having the compliance test suite sequences that we provide on. Here I'm showing a screenshot of an enum that basically is used to run these compliance test suites with a snapshot of a code that runs that. Also, the assertion coverage. Assertion coverage is basically the illegal scenarios. So you could use our VIP to hit these illegal scenarios, all of them, and then check how your IP or dot will behave in these scenarios, how it will recover. Here you can see multiple screenshots, the enum for the compliance test suite, a snapshot of a code related to running these compliance test suites, and finally, a snapshot of our coverage from a test run that we did. Finally, it seems like I finished a little bit early. I'm opening the ground for any questions that you have.